All right, so hi everyone. I'm Shira Chapman from Ben-Gurion University, and I'm going to tell you about quantum chaos, operator spreading, and a surprising link to black holes. I come from physics, but I did make an effort to make the talk accessible to people outside of physics. You should feel free to stop me at any point. There are parts of the talk that I could skip, so I could adjust, and I would rather people being able to follow. I should also say before I start that my main research focus is actually the last bit, so the link to black holes. And I'm certain there might be some bigger experts on the audience on quantum chaos, so you can also interrupt me with corrections. All right, so... אני בטוחה שזה לא הטייפ האחרון על השקופית. All right, so I start with classical chaos. I'm sure that's a term familiar to many of you. Often at the popular level, it's introduced starting from the question, does the flap of a butterfly wing in Brazil sets off a tornado in Texas, which is actually the talk titled by some scientist from MIT named Edward Lorenz from 1972. And this guy essentially showed that the equations describing airflow are extremely sensitive to initial conditions, namely that small differences in initial conditions can grow into very large differences in later behavior. So that is what we call classical chaos. Put more precisely in equations, we expect that if we have two trajectories of, say, a particle that differ by a small amount at initial state, in a classically chaotic system, the later position of the particle will be exponentially sensitive to changes in the initial conditions. Well, this lambda L over here that will play a role at many later stages of the talk often goes under the name of Lyapunov exponent, and it essentially means that the trajectories separate when it's positive. So this leads me to the question, how does this kind of chaotic dynamics manifests itself in quantum system? We are, after all, a quantum center. And it turns out that the answer is non-trivial. So it's non-trivial to generalize the notion of extreme sensitivity to initial condition in a straightforward way to the quantum world for probably many reasons, but these are two. So the first one is that it's impossible for us to bring initial conditions of trajectories as close as we want together because of the Heisenberg uncertainty principle, so we can't localize particles as close in phase space as we want. So that's one reason. But you could think of like kind of a naive generalization. Let's think of just the vectors that describe a quantum system, psi of 0, and ask if I had two vectors that are very nearby each other, how do they deviate as the system evolves in time unitarily? That would kind of be an equivalent in the quantum work, but that doesn't work as well since unitary evolution preserves inner product, so the distance between initial state and final states in this sense is exactly the same. So quantum states do not separate like classical trajectories. So what can we do? How do we think about chaos in quantum systems? So that's going to be the subject of the talk. The plan of the talk is the following. So I'm going to start with a simple example of the idea of taking chaos from the classical to the quantum world. Simple idea with a single particle. I will then describe what this means about the spectral statistics of the Hamiltonian of a system. And then I will move to more modern approach to studying chaos in many-body quantum systems, which mostly focuses on time-dependent signatures, so dynamical signatures, including the idea of operator spreading and out-of-time ordered correlation functions, the OTOC. And I will talk about information scrambling, so everything Dorit advertised, hopefully. I will then move to discuss this kind of surprising relation to black holes that goes through the SYK model. And I'll have a comment about the relation to pseudo-randomness at the end, hopefully. But please do feel free to stop me at any point. All right, so starting with the first bullet point, classical and quantum chaos. Let's take a simple example with one particle. That's an example with which people demonstrate often the idea of moving from classical to quantum chaos. So imagine that we have a particle that moves freely on a billiard table along straight lines with a constant velocity and is reflected like mirror-like at equal angles at the boundaries of this billiard table. It turns out that the shape of the billiard table can determine whether the motion of the particle is chaotic or integrable at the classical level and also at the quantum level. So at the classical level, just like we said before, certain shapes which are more symmetric, for example, a rectangular billiard table, will not have a very high sensitivity to initial conditions. So for instance, two particles that start very nearby each other will not deviate significantly as they move on in time, while other shapes of billiard tables, like this stadium-like shape, made out of two circles and lines, will be very highly sensitive to initial conditions. So trajectories that start very nearby each other, like those, will end up completely different after a certain amount of time. So what is the equivalent quantum problem? The equivalent quantum version of the same problem is the following thing. So we need to move to a probabilistic world. We look at the whole problem is phrased in terms of a wave function, which is essentially the probability amplitude to find a particle near position x. And I know that we all many people in this room work with just simple spin systems, but it's this psi of x, the probability to find a particle near position x, is just a continuous analog of the alpha and beta when we write a spin up, spin down superposition. All right. So now the equivalent of diagonalizing the Hamiltonian is simply to find the eigenvalues and eigenvectors of the Schrödinger equation for this wave function when setting it to 0 on the wall of the cavity, so on the wall of this say stadium or the shape of the billiard table. And so we can ask, what can we say about the distribution of the allowed energies solving Schrödinger's equation, and about the shape or the form of these probability distributions to find the particle at any position x when the classical system was chaotic or when it was integrable, so simple. It had a lot of symmetries. All right, so this is just kind of a pictorial thing. If I take, for example, one of the eigenfunctions, one of the equivalent, the eigenvectors of this system, and I just draw them. On the left, for the case of a billiard table, which is integrable, so it has non-deviating trajectories at the classical level, and on the right for this kind of cardioid shape, which has trajectories that deviate exponentially at the classical level, I will see a very different structure, very different probability to find the particle at different places on this cavity.
Sure.
Yeah, sure.
Where are the initial conditions in this description? Like you said, the Schrödinger equation, but where's the place and position and I don't know, momentum that you start with for your ball? Where does it appear?
Yes, I think the point is that you should think about it a bit differently. It's like diagonalizing a Hamiltonian. Right? When you look at the Hamiltonian and you ask what are the eigenvectors and what are the eigenvalues, right? What are the energy levels, you don't ask about initial conditions. They are kind of like, they describe states, energy states of the system. So you are moving to this description. If you take this kind of H bar thing to 0, then the probability to find a particle at every location will become kind of localized, and it will start resembling trajectories again. But the way to think about it is, right, you usually don't ask about, you can then set your system in an initial vector and evolve it in time. That you can do. but there are many. But the initial vector you start with is a superposition of these kind of eigen.
So you're diagonalizing the Hamiltonian of the dynamics of this billiard ball rolling, or what? This
yeah,
is just.
You should think. So you should think of this thing over here is essentially what you. It looks. If you look at it, you will recognize it. This is momentum. It's like p squared over mass.
Okay.
So this is the Hamiltonian. It tells me if I give you a probability distribution of finding the particle at every location, what is the associated energy? And you're looking for eigenmodes of this equation. It's very, very similar. Again, you see this psi of x. What is it? It's really the analog of the alphas and betas, right? So you are trying to find.
Yeah, psi of x is fine. That's not the.
The way the analogy. This is one way to sort of take classical randomness, or in this case chaos, to the quantum world. So the way Shira is doing it, and the way that it has been done for a long, long time, is to look at the Hamiltonian at the billiard ball, and place infinite potential outside of the billiard ball. Okay. So, and then you get a Hamiltonian. Out of the table.
Yeah, sure. That's like
and then you get a Hamiltonian with some boundary conditions on the and you solve for that. And the point is that the eigenvalues are going to behave according
like
to
a steady state. This is like
just you solve for the eigenstates of this Hamiltonian. It's a matrix. Infinitely.
Because, like. When I think Schrodinger equation, it's like I think time evolution, but here you're just what you're getting is just
It's
like
a stationary. Yes.
Yeah, so you're like it's like Hamiltonian of psi plus 0.
Yeah, exactly.
Okay.
Exactly. Or not zero. Well, equals e times psi. Yeah, it's exactly h psi equals e psi, the equivalent in the continuous version. Just think that instead of spin up, spin down, I have this like infinite list of many, many, many possible positions.
I feel like the dimension of the Hilbert space is not what's like sort of.
Bothering me. It's just that I wasn't sure that I understood like what you're actually computing. So you're computing like so a solution to this thing, like an eigenvalue of this Hamiltonian, is going to be like some type of it's going to be a quantum state such that if you start your system in this quantum state, it's just going to sort of stay there.
Yeah.
Right. You just like put on the billiard ball. It like actually corresponds to like a superposition of like positions of balls with different trajectories and whatever. And this is like it's going to be like a.
Exactly, it's like the standing way. That's where it was. Exactly. Yes. Yes. Who is asking? Yes.
Is there a parameter that you take that takes you from integrable to chaotic? Is there like a phase transition here?
No, because I mean, the point is that integrable is. You should think about chaotic is kind of the standard thing. If I just take my pencil and I draw this kind of random table, it's most likely going to be chaotic. To be integrable, you need a large number. You need a number of symmetries. It's not large when it's one particle, but that is the same as the number of degrees of freedom in the problem. So, if you have like this up-down reflection, right-left reflection, or something very symmetric, then you will stay integrable. So you could probably, I don't know, take an ellipse and make it, I don't know, take a billiard table and bring it closer together. I don't know how, yeah.
So a circle would be.
Yeah, isn't it? But like a square.
No, you could shrink my stadium until the upper and right, but I don't. I mean, it's a very sharp behavioral difference, right? So this. So I don't know if you would see it in a smooth way, something. Yeah. All right. Wait. So we had this very nice. So in the drawing just means in black it's very highly likely to find the particle there. It's high psi of x, and in white it's very low probability.
Is this the ground state?
This is not the ground state at all. It's the 2000th. You can find special states that look kind of special, but the generic state that you would find would be kind of spread everywhere if the system is chaotic. So it's this statement that of ergodicity that you cover the whole phase space, you can kind of get everywhere, while for the integrable system, typically it would have some structure, it would be more localized.
Shira,
Is it, sorry for the basic question, but is it obvious that this is a discrete? I mean, you like 2000, like the discrete, like you also wrote it in the equation itself, there was an n there. It is always like that.
I want to say yes.
There are variables. This is quantum physics, right?
Then because of the boundary condition, you also have discrete times?
Yes, maybe it's you should think like the modes of a string because you are folding it into two edges. Then yeah, then the standing waves have like in a. Okay. All right. Good. So what about now the distribution of energies, of eigenenergies, eigenvalues En for this equation on the chaotic and integrable billiard tables? So it turns out this is that's going to be the first diagnostic of quantum chaos in more general systems. So if I take this system and I solve it, and I order the energy levels one after the other, and I look at the spacing between them. So I look at the spacing between each two consecutive eigenenergies. I also do some kind of, there is something called unfolding, which essentially removes the average density of states and leaves the fluctuations that I'm not going to get into too much. But once doing all this, I can ask, do the energy levels cluster or repel? And it turns out that for chaotic and integrable system, the answer is very different. So here on the left, you can see the distribution. So it's a histogram. What's the probability of finding a given S? S, you remember, was the difference between consecutive eigenenergies. So on the left, it's for the circle billiard, so for the integrable system. And on the right, it's for the cardioid billiard, so for the chaotic system. And what you see is that this probability distribution for the integrable system, so for the circular billiard, they have Poisson-like statistics, meaning that the probability of finding a certain gap in energy goes like e to the minus s. And the most important part about it is that it doesn't go to zero when the gap goes to zero. So it means that it's very likely to find very nearby energy eigenstates in an integrable system. It has an explanation, but I won't get too much into it. For a chaotic system, on the other hand, nearby energy eigenstates repel. So the statistics look something like s times e to the minus s squared, which is a function, you see that thing, that vanishes for small s. So it means that it's very unlikely to find nearby eigenenergies. And for this reason, we say that the energy levels repel each other. In fact, this kind of distribution is exactly the one obeyed by Gaussian orthogonal ensemble statistics. And in general, chaotic systems fall into several universality classes for the statistics of their eigenvalues, but they all have this property that nearby energies repel.
I have a question.
Yes.
So the spreading of the energy level and the exploration of the space, do they go together fair and pair? The fact that the energy level spread to your spread go apart, and also the fact that in chaotic setting, the wave function studied for space, is it related somehow?
Yes, I mean, there is also the point is that there is a motivation. The point is that the reason why integrable system behaves, both it's localized, the eigen functions, and the energy levels get closer together. They all come from the symmetries, because the solutions of the equations carry additional labels, and these labels can kind of sit nearby each other. It has an explanation, but I didn't want to get in too much. All right. Okay. Just a second. Okay, this is the one slide about the relation to random matrices. So why did I say that it's related to ensembles of random matrices? So that's a very simple example. So consider the simple random Hamiltonian made out of three numbers, epsilon 1, epsilon 2, and v, all of them sampled from Gaussian distribution with 0 mean and variance 1. You can study the eigenvalues of this matrix, and you can convince yourself relatively easily that the eigen states will be distributed exactly in this way, which was what we saw before for the chaotic systems. So essentially the same effect of level repulsion and so on. And as I said, it's the same distribution as we saw for the chaotic billiard tables. This is also true for large matrices and a large number of energy levels. So essentially, there is a relation between how energies distribute for random matrices and for chaotic system. We say a system is chaotic when the energies are distributed in a way that essentially looks like some random ensemble of matrices. All right.
Shira, there's something I don't understand. There seems to be some behind this notion of approaching the GOE random matrix theory. There seems to be some n that you take to infinity, right? Or something that gets better and better approximation. Also, when you think about distribution, it seems like is that not the case, that you have some kind of a better and better approximation, or is it the claim that for a billiard ball, a particular billiard ball, you get what do you mean by distribution for a particular billiard ball?
So I mean that if I take this, I may take a random matrix, I compute the energy levels, I compute the difference. There are just two energy levels, right? It's a 2 by 2. I do this again and again, and I plot these on a histogram.
That I understand.
I will get a histogram that looks the same as the one of the billiard table from before. So I will get.
But the billiard table from before, it's just discrete. It's just what do you mean by distribution for that?
Right. So in that case, I have many. Right. I have many solutions to the Schrodinger equation. I mean, you see, the 2 here plays the role. It's a single particle, so it has like kind of.
Okay,
so
that's the answer
but,
that you gave Zvika?
Maybe, yeah, but it's true in general. The idea of looking close to the statistics of random matrices is true also for systems with many degrees of freedom.
Okay.
But you understand, right? Even though it's a billiard table, it has many eigenmodes and many eigenenergies. So I can look at the differences between any 2 consecutive pair and start throwing them on a histogram. It's a single Hamiltonian. It's just one billiard table.
I see.
There's
Okay.
nothing random about it.
Okay, then you go to infinity for
Yeah.
them. I see.
Exactly. All right. Okay. So from this, so this is nice because the system has kind of a classical analog, so I could explain everything in a nice pictorial way. But many of the systems that we study in quantum mechanics don't have such classical analog. But nevertheless, the idea is that people consider this Wigner-Dyson-like statistics of the level spacing, meaning that the levels repel each other, as a defining property of quantum chaotic system, whether they have a classical counterpart or not. And you can ask, I mean, why do I care? I can define many things, right? I can invent a name for a system, say it's chaotic if it has this property. But the point is that chaotic systems have very nice behaviors in various contexts. Among other things, they thermalize. I think Evgeny is going to talk about that. So it's interesting for us to know if a system is chaotic, quantum chaotic. So I give the example here of the Ising spin chain with near site coupling J and transverse and longitudinal fields Hx and Hz. And what you see on the bottom is on the right, there is a case where the system is integrable, so this Hz magnetic field is turned off. And in this case, you see that there is Poisson statistics, so the levels can be very close by together. While for the left case, where Hz is non-zero, it's a kind of more generic case where the system is chaotic, you see that you have this Wigner-Dyson-like statistics and repulsion of the energy eigenlevels. All right, so now I'm going to move to the more modern signatures questions about that. No?
Can I ask you?
Yeah, sure.
the importance for the properties to emerge is just the boundedness away from zero, or do you actually need the whole this kind of picture?
I mean the whole kind of picture. It's very universal, so it falls on these exact curves. But you can see, I mean, it's an intuitive picture because I'm drawing differences of energy levels. If I drew just the energy levels histogram, you would be able to see if they cluster, they tend to be close together, or they spread away. And this repulsion is kind of way to if you just look at in the eyes on the spectrum and not just at the differences, you would see that in chaotic systems they repel. So it's a way of identifying.
So why is case B integral if hx is different from 0?
I think it has some symmetries. Who is asking?
Yes.
Yeah.
Yes.
It has to do with the symmetries, but I think that there might be people in the audience that can answer this better than me.
What was the question? I couldn't hear.
If he's asking why the...
different from 0 integrable?
I didn't hear. Sorry, one person. What did you say?
מה הוא אמר? לא שמעתי.
לא שמע אותך. תחזור על השאלה.
No, me.
Why is hx different from 0 integrable?
Because in this is to, I don't know if she didn't mention, but you need to resolve the symmetries, as you mentioned, in fact, of the system.
What symmetry is the...
No, here, if you, for example, don't have one of the two fields, then you will have other symmetries of the system. Let's say you flip the spins, or you flip the chain, and then it looks the same. Then if some of the parameters are not there, then you need to further resolve the symmetries. And then in each of these sectors, you need to solve the statistics.
Too complicated.
Okay.
It's okay.
Shira, just like some of us, at least one of us, doesn't really know what an Ising spin chain is. So if it's important, then if we need to know, then maybe you can tell us.
Yes, so it's a system with n spins.
Okay, so n qubits, yes.
N qubits, yes. N qubits. Z is sigma Z. I don't know.
Yeah, that's fine. That's fine. Pauli's are
That's
good.
the Hamiltonian.
But what is
it's a
H?
Sum,
What is H sub x and H sub z?
They're couplings, values of coupling.
Oh,
that
okay,
you can tune.
okay,
You can
okay,
tune
good,
J,
good.
you can tune HX and HZ.
Okay,
and
good.
you just build this big matrix and
Sounds good. So
diagonalize it.
it's just a one-dimensional string of qubits where each two are like sort of interacting together, and then you also have like these terms that are like sort of.
Exactly.
Okay, thanks.
Is there any connection or thought of relation between this notion of chaotic systems and some notion of complexity from the point of view of computational complexity of the evolution?
Yes, there is, but I left it out for time, and I think I should still leave it out for time.
Okay.
But
I'll ask you.
I will move anyway. I will move now to the dynamical signature. So after I talk about that, might be a better point.
Okay.
Okay, so all this is pretty old. The idea of understanding if a system is chaotic, quantum chaotic from its spectrum. But many of you know, of course, that spectrum is very hard. A full spectrum of a big system is very hard to compute at the numerical level. But we are still very interested in identifying chaotic systems in many-body physics for the reasons I mentioned earlier. So more modern approaches try to understand if a system is chaotic by focusing on dynamical diagnostics, namely signatures that depend on the time evolution. So now I'm going to go through several of those. I'm going to start with operator spreading, then I'll talk about out-of-time ordered correlation function. I might skip the last bullet point, let's see. All right, so let's start from operator spreading. So as I said, we shift attention from the spectrum to now time-dependent properties of the unitary dynamic. So we are asking the question if H is chaotic, quantum chaotic, what are features that I can expect from e to the minus IHT? And one of these ideas is the idea of operator spreading. So the question to answer is whether there is a difference between chaotic and integrable system in how the support of a local operator, W, spreads with time evolution. Meaning that if I take a localized spin operation, W, and I evolve it in the Heisenberg picture with e to the minus IHT, e to the plus IHT on both sides, What will I see in this evolution that will distinguish chaotic from integrable systems? It's some kind of quantum version of the butterfly effect, because we are putting a small localized perturbation, you can see also in the picture, and then we are asking how it spreads, how it influences the system at later time. So this is the idea of operator spreading. Even though the systems I'm interested in evolve with a fixed Hamiltonian, to kind of understand what to expect from these systems, it's useful to first think about a simpler cartoon, which is a random unitary circuit. So it turns out that chaotic dynamics is modeled well in terms of random circuits. And that means that chaotic dynamics looks just like the eigenvalue distribution looked like random matrices. The chaotic time evolution looks very similar in terms of its signatures to what happens when I evolve not with a fixed Hamiltonian of the system, but with a sequence of random gates. So imagine now that I look at the following, so the same question I asked before. I have a localized perturbation W, and I evolve it from both sides. I evolve back in time, then add the perturbation, and then evolve forward in time with a sequence of random gates. So heuristically, I have this unitary here that is a product of some random choice of gates. Then I put my perturbation, and sorry, other way around. I first evolve back in time, I put my perturbation, and then I evolve forward in time. It's really kind of asking how would the system look had I inserted the perturbation some time t in the past. And the question is, how does the support of the operator spread? How does it start influencing the rest of the system? So I have this cartoon on the right. You see 10 spins. Sorry. Oops. Here's the perturbation, W. And now as time evolves, I randomize some simple gates, 2-qubit gates, and I apply them to the perturbation. So after one time step, let's say I have part of these gates here, and the exact inverse gates with the u of minus t, so with the inverse evolution. So if I didn't have the perturbation at all, the forward time evolution and the backward time evolution exactly contain inverses of each other, so they would cancel completely and there would be no support of the operator. But since I added the perturbation, some of these gates, which are in fact the inverses of each other, you see g and g minus 1, some of them would not cancel because they don't commute with the perturbation. And so say after one time step, I'm going to now have the support that has extended from 1 qubit to now 2 qubits. And then after 2 time steps, I would start caring in terms of support or which parts of the system have been influenced. I would care about all the things that did not commute with my original perturbation, but also with gates that did not commute with my original perturbation. So then the effect would spread further away, and further away, and further away, and so on. So there's some kind of light cone picture that shows which parts of the system have been influenced by the perturbation.
Just goes in the future, not in the past.
You don't like the time that goes in both directions?
How come it goes to the past?
Yes, because you have to remember that I'm not really drawing the evolution of a state, but I'm drawing the evolution of an operator, and an operator has 2 sides, right? It's a matrix. Yes. So imagine that I would like kind of multiply by a bra on the left and a cat on the right. The cat is evolved right with e to the IHT, and the bra with e to the minus IHT. So you can say, why are you bothered by this?
I think I'm beyond redemption.
That's never true. Maybe Dorit can, I don't know.
I don't have an immediate answer.
What?
I don't know how to answer this, so we could discuss it. But I wanted to ask, probably you're going to say, you said that it's being modeled by, so chaotic systems are being modeled well by random circuits. You're going to make this more precise? Is there a theorem that says something about it, or?
I'm gonna make this more precise in terms. In terms of explicit examples, I mean, you can look at explicit examples of chaotic systems which are chaotic in terms of their spectrum distribution, and you will see the same signatures that you see from random evolution. I think it's more trial and error
What
kind of thing.
signatures are you looking for?
Yeah, so now, okay, so this is kind of a heuristic, right? That's very heuristic picture, operator spreads, what is the thing I'm computing, right? So yeah, I'm gonna put that in a precise sense in a second. All right. So as you said, right, this kind of spreading of an operator is more of a heuristic picture, and that was just to kind of understand what I expect. But in general, the spreading of the operator can be characterized in a very precise way by commuting it with another operator. So I can ask how far did my operator spread inside the system by asking how much it starts failing to commute with another operator that was originally located far apart. So if I have, say, a spin chain, whoops. If I have, you see a kind of a spin chain, I put one operator in one site, and I evolve it with time, with this Heisenberg time evolution. I can ask how much does it fail to commute with an operator that is localized far apart. That is exactly what defines this quantity called the out-of-time ordered correlation functions, which is essentially the commutator of this time-evolved operator with an operator localized elsewhere. Trace norm, square to make it positive, and so on. So if these two operators, W and V, W, which is the one we evolve in time, and we want to assess how much it spread, and V, which is the kind of the test operator, are initially far apart, then the auto will originally vanish. But as
zero?
Sorry?
Should be C of 0?
It should be C of 0, absolutely, yes. I said it was not going to be the last typo. And as W of t spreads, it eventually fails to commute with V, so we get a positive kind of auto spreading. If we have a semi-classical limit for the system, this auto is related essentially to, so in general, commutators are related to Poisson brackets, which are no other than the original idea of sensitivity to initial conditions. They are really the quantum version of the variation of the initial position with respect to, so of a final position of a particle with respect to the initial position. So we really do expect that in systems that have a semi-classical limit or very close to being classical, we expect this auto to spread exponentially. All right.
Okay, sorry, can you share with me?
I can. Yes, sorry. On which point? On the
About, so you said that auto measures operating spreading in the sense that you do expect that it will be non-zero when there is intersection.
Yes, and I expect it to become large when the kind of the wave front of the operator W crosses the.
So you said something about exponential.
Why would it be exponential? So not in every system, but in a system that is very near to a classical system. The idea is the following. So imagine that I take, I don't know, I go back to my billiards or whatever, it's a particle that has position and a momentum. And I take my operator W to be x hat, like the position, and the operator V to, what did I do? It's supposed to be there, it's flipped here. But the W would be x hat and V would be P. So essentially, a version of the auto could involve a commutator of momentum and position at time x. That would be, it's just rewriting W of t, V of 0. And that I think requires knowing how exactly the transition from quantum to classical is made in semi-classical systems, but it's done, I mean, basically the way to motivate how to move from a classical thing to a quantum thing is with the Poisson brackets. The Poisson brackets are it was just kind of comment for people familiar with it, but it's essentially the derivative of the first operator with momentum, second with, right? So if you just differentiate the first guy with respect to momentum, you're going to get 1, and the second one you're going to get the deviation of the initial condition.
Wait, yes, he also.
I think there is a very nice theorem known as Lieb-Robinson.
Yeah, there is Lieb-Robinson bound,
which
sure.
characterizes how the commutator behaves. And it shows that there is a cone, and the commutator is non-zero inside the cone and outside the cone. It's exponentially small.
Right.
But this is talking about exponentials.
No.
It's
This is not.
estimate on the commutator of two operators.
It's not related. It's wait. Let me say just 1 second. There is the Lieb-Robinson bound that bounds the size of the commutator. It defines the wavefront. The wavefront can still be kind of a linear propagation, whether it's exponential. I mean, the question of what combo of position and time, x and t, is involved in the growth of the OTOC. It can be linear, it can be exponential, it can always, but the wavefront would appear. The Lieb-Robinson bound gives you bounds on how fast it can spread. But the point in the last bullet point is another point. It's just that when you have a semi-classical system, you expect an exponential growth of this OTOC at early times. I don't know. Yeah. Sorry? Yeah. Exactly. So there is a Lyapunov exponent in systems that have a semi-classical limit. Exactly. Sorry. What? I don't know what I will do. I will think while I explain. So. Right, so as I said, in systems with a semi-classical behavior, the OTOC, so this commutator, behaves exponentially for a certain period of time. This certain period of time is between the local dissipation time and what's called the scrambling time, so the time at which the perturbation has scrambled throughout the entire system. And this is when this out-of-time ordered correlator becomes of order 1. Which for semi-classical systems, so when h bar is small, it can be a large time, but in kind of standard spin system, it can also be a regime which is hidden completely. So you don't always have this separation, only in systems with the semi-classical limit. This Lyapunov exponent is bounded in thermal systems by 2 pi times temperature. When you don't have a semi-classical small parameter like h bar, say in an Ising spin chain, you can still look at the OTOC and see how it behaves. It becomes large when this kind of wave front of the spreading operator crosses the test operator, and that kind of becoming large can be used as a diagnostic of chaos even in systems without a semi-classical limit. All right, and then I have this kind of, the last point, which is that all of this is kind of quantum chaos phenomenology. So we assert that these are probes of chaos. They are presumably necessary but not sufficient to have quantum chaos in the sense of the spectrum, based on many examples that we've tested. But the spectrum is, again, hard to compute. So we are looking for some signatures that will indicate that the system is chaotic or not. All right. Sorry.
What did you mean by well?
It's the, yeah.
That eventually it goes away.
Yes. All right. Now, I think the point is that I'm a bit short of time, so I also wanted to say a few words. Yes, I might not, well, I don't know. Maybe I will do the black holes. How much time? I don't have a lot of time, right? I have more than 15 minutes? Yes. Okay, okay, then good, very good. All right, so another diagnostic of chaotic evolution is that the quantum information in a local operator W efficiently spreads over many degrees of freedom in such a way that it cannot be recovered easily. So this is another thing that we expect about, in this time, about entanglement, measuring the spread of information in a quantum system. So the idea is the following. So everything measured in terms of the von Neumann entropy. We take a pure state psi of t, and we consider a small subregion of it, and we want to ask what happens with time evolution via a chaotic Hamiltonian to the entanglement entropy of a given subregion. The initial state is not an eigenstate of the Hamiltonian, so it evolves interestingly in time with our chaotic Hamiltonian. And how does the von Neumann entropy of a small subregion behave with time? So at first, if we take a state which is simple, in the sense of being very weakly entangled between the different sites, the entanglement is initially small, but as time evolution progresses in a chaotic system, it creates more and more entanglement across the cut. So I don't know, if I had an initial perturbation, it would spread around, and it would, knowledge about this perturbation would be kind of everywhere. So another signature indeed of chaos in chaotic system is this growth of the entanglement, the idea that the entanglement grows linearly at first and saturates to the maximal allowed value by the subsystem size.
So are all these known, is anything known rigorously?
No.
So what is known rigorously? Is it known, for example, that chaotic systems have this linearity behavior of information traveling?
I think you can explain, I mean, you can, for example, if there is some kind of quasi-particle description, it's relatively easy to motivate or to explain. I'm happy.
Is there even
if
like
people want to jump in and say, I'm happy. I mean, it's.
So I don't know. I thought I had like a similar question. So tell me if this is the same. So we had this like definition of what it means to be chaotic, where like the gaps between the energy levels are like have this distribution or close to this like distribution. And the question is, why does it follow from this property that like you have this behavior of the entropy? Is there even like a heuristic description of why the entropy is supposed to grow, even just because the gaps between the like? Is this something that you can tell us? Is there like some?
So for example, if you have a system with what's called a quasi-particle description, it means that you can kind of think about it. I feel like I don't know. There is a tension between how much to wave hands and but
maximal hand waving.
Imagine that your system consists of many bell pairs,
okay.
entangled pairs that you put in your system, and they start moving in different directions. What will this is not a bad description for certain systems that have this kind of quasi-particle-like effective behavior. The point is that these bell pairs that move in different directions, at some point, some of them will cross the cuts.
Okay.
So initially they were nearby, but they will cross the cut of your subregion. So one of them will be out, one will be in, and this will contribute to the entanglement count.
Right. So somewhat in my language, that would be like an example. Is there like a reason why there's a rule that whenever there are gaps between the energy levels, then the entropy of a cut is supposed to grow? Like even in like, I don't know, some... Is there like a reason to suspect that it would happen even, or if it's just like because we're looking at specific systems that have this property and we see that they also have this other property, and this is related to what you're asking, right? Or so the answer.
Yes. I feel like I'm not answering this formally enough, but we can look. I mean,
yeah, sure. I was even like even like a very high level intuitive reason of why something should happen, other than saying, well, if there's gaps, then it's like scrambling, so stuff should.
And another pressing point from the rigorous.
Let's come back that
I wanted to ask again, is there anything known about the relation between random matrices and random circuits and chaotic systems? Chaotic systems. I mean, so you basically said that these chaotic systems are more than dwelled by random circuits, and I don't really understand the statement very well. What do you mean by that, other than the fact that it's
that it looks.
I don't even know what it means that it looks similar.
No, it means similar. No, it means that it looks similar means that if I instead of my exact Hamiltonian e to the IHT, I started randomizing 2 qubit gates and putting them together. And I did one layer, and I called this would be my unitary at time 1, then another layer, my unitary at time 2, and so on, in a discrete way. This is an invented time evolution that I drew from some ensemble. This would behave in the sense of I would draw the entanglement, and in all the senses that I described, it behave.
Yeah, so in what senses? In the sense of how the auto grows?
In the sense of how the auto grows, in the sense of how the entanglement grows, yes.
I see. Okay.
And yes, I'm sure that you can do some kind of, you can do combinatorics
And
on
is
these
it
gates, and
known-
you will be,
Is it known, for
to get
example,
convinced.
for random circuits, is anything rigorous known about outlook and about the information?
Yes, yes, yes.
Yes.
There are results, yes, yes. Yes. Okay. Yes.
Is it true also for like general local operators? And not only like entropy, you look at the local observable, would it kind of be the same, just kind of change and etc., or just
You can think, the idea is to start with a state that is not an eigenstate of your Hamiltonian, because that one would evolve not in an interesting way. It's what is called a quench. So you can do different things. I mean, one of them would be to start with an eigenstate of your Hamiltonian, but insert a local perturbation, and then evolve that guy in time. Another one is to start with an unentangled state. But yeah, the point is that you would see kind of this linear growth in this type of quench state, which are not eigenstates of the Hamiltonian.
for any local observer, like general, I don't know, and like just like summarization.
Yes.
So if the entropy goes to maximum, doesn't it mean that like every local observable is just going to see a maximum atomic state, or is it like something deeper? Like if I hit like maximum entropy,
Or something very similar to it. Well, not yeah, or to a thermal state. Something very similar to a thermal state. Yes, exactly. All right. Thanks. Yeah, I had this nice small comment about the fact that these ideas of scrambling information and the fact that information is kind of dispersed everywhere in terms of unitary evolution of chaotic system was used in very tiny, cute toy models the idea is not for tiny cute toy models, but implemented experimentally in tiny cute toy models to do some kind of many-body version of quantum teleportation, where instead of 3 qubits, one takes 2 big systems and a message, spreads the message through the system via time evolution, then couples it to another system.
What are you not talking about?
What?
Can you start from scratch?
Yes, I don't know. The point is that I'm. Let me think for a second. Give me a second to plan my plan, and then going to be a disaster.
I think 10 more minutes. It's
Yeah, no, it's fine. I'm just debating with myself what to skip. Well, okay, we will get where we get, I guess. Yes. All right. Okay, so I wanted to mention that this idea of information scrambling with chaotic Hamiltonian evolution is used in a new mechanism that people found for teleporting a message between 2 systems via this scrambling. So instead of the usual thing where we take a message and we try to teleport it between Alice and Bob, having just a bell pair shared between them, we start with 2 big systems, and the mechanism for the teleportation, instead of being the standard teleportation mechanism, involves, after injecting the message, scrambling it over all the degrees of freedom of one system, and then very weakly coupling this system to the other system, and then unscrambling the information on the other side. So it's a very kind of interesting method to teleport things between big systems, which can identify the kind of scrambling dynamics. If the system is highly scrambling or if it's chaotic, then the message will pop out on the other side. If it's not, it will not pop out on the other side. It's kind of it's a kind of a cute thing that has been also realized in very small toy models experimentally. And we also have worked on that with my student. Yes, but I will not get to the black holes.
Why?
No, because I want to. Yeah, because I want to get to the link to the black holes. I'm sorry. I thought that 35 slides would be reasonable, but.
How much time do you need?
2 hours. But I will not use 2 hours. But I'm happy to talk after the talk about that one. I agree, it's very interesting.
We can't get back to this. You can just talk 10 times faster.
No, I don't do that. I will just stop where I get in 10 minutes and that's it. All right. So I'm sorry for capping that part. But okay, we've seen many signatures of quantum chaos in time-dependent signatures, entanglement, the auto, the operator spreading, and so on. And now I want to discuss something bit surprising, which is the link of all these ideas of quantum chaos to black holes and gravity. And I guess you can summarize this idea in one main message, which is that black holes are thermal, highly entropic, and extraordinarily good at hiding quantum information. And for these reasons, it's natural to think about them as chaotic systems. And I want to say, what exactly do I mean by this? So this is more my own line of research, so that I wanted to get there. So how do black holes enter the story? So as you probably know, black holes are massive gravitational objects from which light cannot escape. That's kind of the popular picture. They are predicted by Einstein's theory of general relativity and measured in different waves, including gravitational waves coming out of their collisions. But in many senses, black holes behave like thermal systems with a very large number of degrees of freedom. This dates back to the Bekenstein-Hawking formula from '73, which essentially says that the horizon area of a black hole behaves in many senses or obeys rules of thermodynamics very similar to an entropy. For example, it can only grow and obey something very similar to the first law of thermodynamics and so on. But this is more than just kind of a mere analogy, because it very soon afterwards turned out that black holes actually behave like thermal systems because they radiate. They radiate through a mechanism called Hawking radiation with a temperature that looks like that of a certain thermal body that depend on their mass. Now, the entropy of the black hole by Bekenstein and Hawking is actually a very, very large number. So if you take a black hole of a single solar mass, and there are many constants of nature here. There is speed of light, h bar, Newton's constant. You just plug the number, you will find that the black hole entropy of a one solar mass black hole is something like 10 to the 77. So that's very, very, very large. And we know that in statistical physics, entropies count numbers of states in a system. So there is a question here of what exactly is this entropy representing? What are exactly the states of the black hole that this entropy is counting?
So this should be exponential in 10 to the 77?
Yes.
Yes.
The dimension of the Hilbert spaces.
Yes. 2 to this.
And what is 8?
Sorry?
You said I think every surface area 8?
Surface area of the block.
Right. Another typo?
No, that's fine.
No.
And it turns out that there is a way to answer this question of what exactly are the states. It's very, very odd, right? Because a black hole is just like, kind of a sphere of a given mass that doesn't have many states. or not conceptually. So what are these states? What is this entropy counting exactly? And it turns out that there is a very precise way of answering this question. And this involves what is called the holographic dictionary, or ADS-CFT correspondence, which gives a very precise way of answering this question, not for any gravity theory, but for very specific gravity theories, where the gravity lives in some sort of box, and this box is what people call ADS space. So these specific gravity theories, turns out, are exactly dual to very specific quantum mechanical systems. And dual, what does it mean? It means that there is a precise dictionary which maps every problem from the gravity side to the quantum mechanical system that doesn't have gravity. Let me just pause to emphasize how surprising this is. In physics, these are very, very, very different types of physics. I mean, gravity and quantum mechanics without gravity are very different types of physics, but there is still a dictionary that we can use for specific gravitational systems to map questions about the gravity to questions about a simple quantum mechanical model. The quantum mechanical model has no gravity, as I said, and it has it has one less dimension than the gravity theory. It's often pictured, so I told you that the gravity in these special theories lives inside the box. The quantum mechanics is often visualized as living on the boundary of that box in one dimension less. All right, so a few entries in this dictionary are the following. So you can see it's just a table. On the left you have the boundary quantum system, and on the right you have the bulk gravity picture. And this just tells you what the dictionary tells us about translating from one to the other. So the three first entries are what you would expect from all my story about entropy and Hawking radiation. Having a thermal state in the quantum theory is simply the same as having a black hole in the gravity picture. The temperature of this thermal state is exactly the Hawking temperature of the black hole, and the entropy is simply the horizon area. This kind of translation gives a very precise way of answering the question about the count of states, because under this map, the number of states involved in the entropy of the black hole, so the black hole microstates, are simply the standard count of states in the quantum mechanical system. And then there are entries in this dictionary that deal with quantum information. And it turns out that quantum information quantities of the quantum mechanics become geometric in the bulk. So for example, the entanglement entropy becomes the area of minimal surfaces in the bulk. The OTOC that we've talked about, the growth of the OTOC, becomes the question about the change in geodesic length in reaction to throwing something into the black hole, a shock wave. And there are other entries, but I won't go into them. Yes, I wanted to focus on the OTOC because that's what we've talked a lot about. Just a second. Yeah, very hard. Okay, I'm just mentioning without saying too much. All these ideas can be made very precise in the example that I give here. I mean, there are many other examples, but a very simple example in low dimension is a two-dimensional gravity inside the box, which turns out to be dual to the SYK model, the model by Sachdevia and Kitaev involving Majorana fermions. Yes. I want to plan just a second. All right. So that's a model involving n Majorana fermions and random interactions between them, sampled from a Gaussian distribution. I'm not going to go too much into details. Let me just say what I wanted to say about the OTOC. So why does this SYK model matches black hole physics? So it turns out that the large number of fermions maps to the many black hole microstates. For the OTOC, if one computes in this model with Majorana fermions, the OTOC, essentially, it's possible to find it analytically at a large number of fermions. and it indeed behaves kind of exponentially with a Lyapunov exponent of 2 pi over beta, which is exactly saturating the maximal bound on chaos. So that's why you will often hear people saying that the SYK model is maximally chaotic. And it turns out that if you compute the equivalent quantity in the gravity theory, which is the geometric influence of an early shock wave on later probes, you will find exactly the same Lyapunov exponent of 2 pi over beta. This has to do with some blue shift of a perturbation as it falls towards the horizon of a black hole. All right, you can compare also the scrambling time. How long does it take the system to scramble a perturbation across the entire number of fermions? It's going to be something proportional to the inverse temperature times log n for the fermions and to the inverse temperature times the black hole entropy for the black hole equivalent calculation. So the things match.
Shira, about the previous slide, so the SYK model has various variants, right? So you're talking about the 4 local or the many body local? The Q is large or small?
Yeah, I'm not sure.
The little Q, the Q body interaction?
Yes. So I'm talking about Q doesn't have to be large, but N. So how does it work? Look at the picture on the right. You have these N Majorana fermions, right? And then you group them in groups of Q.
Right.
And for every group of Q, you randomize coupling from the Gaussian distribution with 0 mean and certain variance. It's not particularly important what is Q. I mean, you can do it for every Q, but N has to be large.
Yeah, I just know that there is a double something. That's so you're talking about Q, which is fixed.
Q, which is fixed, yes.
I see.
Can be N.
It can be, but in what you're talking about the fact that
it's nicer. You can solve certain things analytically, even more analytically. Sorry, there are different levels of how hard the model is to solve, right? I mean, you can solve it completely analytically, you can solve it numerically, but not with the complex. It doesn't become harder to solve with increasing n or with increasing size of the system, and you can solve it in a way that like you usually solve spin chains, which becomes harder and harder the bigger the system. So for the relation to gravity, so n goes to infinity is the thing that makes it solvable in the sense of not being hard to solve when the number of fermions, there's a kind of analytic-like solution. For the relation to black hole, you can have any Q. But it's even nicer, the solution becomes even nicer when you take also Q to infinity in this double scaling limit. That's true.
So basically, the SYK with the fixed Q is an example for an exact, for a provable ADS-CFT correspondence?
Yes, it's not exactly, it's the low energy limit of the SYK. Yes, it's an example for a provable ADS-CFT correspondence, yes.
Okay, and for the SYK model, you can prove you can prove the chaotic.
You can map exactly the partition functions and yeah.
The autok being the maximally increasing and all that.
Yes,
this is known for SYK and it's also known.
But you understand, of course, that it's not the desirable thing that you gravity in low dimensions very degenerate. So because we come from our end goal is to understand how problems in gravity by translating them to quantum mechanics. So it's not as ideal as you would want. It's very degenerate, the gravity in this model.
So you can deduce from the SYK chaotic behavior, you can deduce a lot about the low energy behavior in the gravity model, in the ADS, but only for the low energy, and people are interested in understanding things about the high energy?
But it's not this, it's the point that it's about the gravity in low dimensions is the problem. Is because we live in a 4-dimensional world, not in a 2-dimensional world.
I see, okay.
All right, so as I said, they are similar. This had a very nice success in recent years, this relation between SYK and gravity in 2 dimensions in understanding better the information problem. It became kind of famous. It was in all the newspapers. All right, I had a slide about my work, but I think I'm gonna I think I'm going to finish. And a comment about pseudo-randomness, but you can ask me later. So the pseudo-randomness can be used.
Since this is the topic of
Should
the
I say?
day,
Yes.
you should say.
All right. Okay. Fine. So I have a one-slide comment about relation of this story to pseudo-randomness. And so it turned out recently, that one can use ideas from pseudo-randomness to argue that some parts of this dictionary that I mentioned, this duality between gravity and quantum mechanics, are computationally hard. What these guys do, Bulan, Pfefferman, and Vazirani, is that they construct states, pseudo-random states, by taking, very similar to what Zvika mentioned in his talk, only for states instead of unitaries. They take one scrambling time unitary, so a specific unitary which is scrambling, and they place in between this unitary, they place operators which are taken from, they are Pauli matrices, randomly sequenced Pauli matrices. So OL, OL minus 1, O1, and so on, are one cubic Pauli operators which are taken at random. And these states are, so the states formed in this way, or the unitaries formed in this way, are not really random. They are given by a key, but they are almost indistinguishable from random. And what these guys did was to use this type of states to show that there are certain questions which are hard to answer in the quantum theory, but easy to answer from the gravitational perspective. And so by this they claim that the dictionary must contain entries which are computationally hard. So that's a comment about the relation to pseudo-randomness.
Where is the key in this spot, in this setting?
It's the choice of Pauli matrices, the choice of OL, L minus 1, and so on for O1 that are inserted. And you would want to take, this kind of construct and ask, is it hard random, or is it produced by a certain sequence of Pauli matrices? And that is very hard to distinguish from.
Thank you.
All right. So summary. So I demonstrated classical and quantum chaos using billiards. Then talked about spectral statistics of quantum chaotic system and the relation to random matrices. Then I mentioned more modern signatures related to time-dependent signatures of chaos, including operator threading, out-of-time ordered collection function, and information scrambling. I mentioned, though briefly, that these notions are related to black holes via their precise duality to the SYK model. And I also said at the end that we can use pseudo-random states to comment on the complexity of this map, of this duality. So that's it. Thanks for listening. Sorry for going over time.